So for this lesson, we're going to take a look at integral exponents. So if I'm following the pattern like what we did in previous lesson, if I started at 10 to the power of 3 and went 10 to the power of 2, I divided by 10 each time. Just like if I went from the power of 1 to power of 2 to power of 3, I'm multiplying by 10 each time. So if I keep doing this, I find that anything to the power of 0, which we already know, is always going to be 1. Well, once I hit 1, if I keep decreasing the exponent and go into the negatives, then I'm going to keep that pattern of dividing by 10 going. So in this case, I'm going to divide this number by 10 and get 1 over 10. If I keep going, then I would divide it by 10 again and get 1 over 100, which is the same as 1 over 10 to the power of 2. If I did it again, I would have 1 over 1,000, which is the same as 1 over 10 to the power of 3. If I'm doing the same process with 3, I'd start at 27, which is 3 to the power of 3, and then divide by 3 to get to 9, divide by 3 to get to 3, divide by 3 again to get to 1, and then once I get into the negatives, I'm going to divide by 3 again, so 1 divided by 3 is just 1 over 3. That number divided by 3 is going to be 1 over 9, which is the same as 1 over 3 to the power of 2. And keep going, and I get 1 over 27, which is the same as 1 over 3 to the power of 3. So if I'm following the same process, regardless of what number or variable it is, if it's to the power of 0, it's 1. If it's to the power of negative 1, it's 1 over that number. To the power of 2 is 1 over that number squared. And to the power of negative 3 is 1 over that number to the power of 3. So if I need to rewrite with positive exponents, then all I'm going to do is I'm going to, in order to make the exponent positive, move the base into the denominator and make the number positive. The same is true with 3 to the power of negative 5 is going to be 1 over 3 to the power of 5. And a to the power of negative n is going to be the same as 1 over a to the power of n. If I'm thinking about this in terms of a double negative exponent, well, anytime that I take a number or a power divided by a power with the same base, I always subtract the exponents. But what happens if I'm subtracting more fives than what I have on the top? Then I'm going to cancel out the common factors on the top and the bottom, and I'm left with no 5s on the top, but I have 3 5s on the bottom. I can say that, well, if I divide everything out of the top, it's just going to become 1. And I'm going to have 5 to the power of 3 on the bottom, which means that I'm going to be left with 1 over 5 to the power of 3 is 125. If I'm using the quotient law, then if I have 5 to the 4 divided by 5 to the 7, it's going to be 4 minus 7, which would be the same as 5 to the negative 3, or 1 over 5 to the 3, which is still 1 over 125. So the results in examples A and C are examples of a general rule when a base is raised to a negative exponent. If I said that I had a to the negative p, it would just be 1 over a to the p. If I'm going to give them simplified with positive exponents and then evaluate to actually solve their value, it's basically exact same as what I did in C. First thing I'm going to do is I'm going to move it into the denominator and make the exponent positive, and then solve the exponent. Same thing with example 2. I'm going to move it into the denominator and make the exponent positive, and then I'm going to solve the power. 3 to the power of 2 is 9. Same thing with example 3. It's going to become 1 over 4 to the power of 3, which we should know is the same as 1 over 64. If I have a negative exponent in the denominator, then that is the same as dealing with a double negative. If I'm using the rules for division of fractions to show that 1 over 4 to the negative 3 is equal to 4 to the 3, then that would be the same as 1 divided by and 4 to the power of negative 3 is going to be 4 to the power of 3 over 1. Which means that all of this is the same as 4 to the power of 3. So, just like how if it was in the numerator, or by itself, it moved into the denominator, if it's already in the denominator, to get rid of the negative, I move it into the numerator. And we see the simplified examples of that here. So, if I'm going to express these with positive exponents and then evaluate, then I'm going to say that I'm going to take 4 to the power of 5 and 4 to the power of negative 3, and because they're being multiplied, I'm going to add them. 5 plus negative 3 is the same as 4 to the power of 2. There's my positive exponent. And then when I solve it, it's just going to be 16. In the second case, for b, if I have 3 to the 2 and 3 to the negative 5, then I add 2 and negative 5, and I have 3 to the negative 3. To make that a positive exponent, I'm going to say it's going to be 1 over 3 to the positive 3, and then when I evaluate it, I get 1 over 27. For example C, to make this negative exponent positive, I'm going to move it into the numerator. And I'm going to have 2 to the power of 5 over 1, which is just 2 to the power of 5. And then 2 to the power of 5 is 32. For example D, if I have negative 7 minus negative 5, be careful because of the double negatives. Minus a negative is the same as adding. So negative 7 plus 5 is going to be 6 to the power of negative 2, or 1 over 6 squared, which is 1 over 36. And remember, if I'm doing my power of a power rule for E, then I'm going to take 3 times negative 1 is 2 to the power of negative 3, which is the same as 1 over 2 to the power of 3, or 1 over 8 when I evaluate it.